What if the most complex problems in computer vision could be solved not by building bigger, more specialized models, but by simply reading the answers directly from what we have already learned? Welcome to a new chapter in artificial intelligence, where the focus shifts from creating endless distinct tools to mastering a single, unified source of knowledge. Today, we are exploring a transformative movement in generative AI that is reshaping how machines see the world. We will uncover how dense prediction tasks, like estimating depth or separating foreground objects, are being revolutionized by a pretrain-and-read approach. We will see how video generation models are evolving into general-purpose learners that unify diverse visual tasks. And we will challenge the common belief that complex verification methods are always superior to simple sampling. Stay until the end because these findings don't just improve algorithms. They fundamentally change how engineers deploy AI in the real world, from autonomous vehicles to medical imaging. For decades, the field of computer vision has been fragmented. Engineers and researchers have traditionally built specialized models for every specific task. If you needed to estimate depth from a single image, you trained one model. If you wanted to detect key points in 3D space, you trained another. This approach, while effective, created a landscape of inefficiency. Each model required its own training data, its own computational resources, and its own maintenance cycle. Furthermore, the standard practice for handling uncertainty during inference often relied on guided search methods, complex, multi-step algorithms designed to verify results repeatedly. While thorough, these methods are computationally expensive and slow. The core problem is that we have been treating vision tasks as isolated islands, forcing us to constantly rebuild the wheel rather leveraging the vast ocean of knowledge we have already accumulated. This fragmentation limits our ability to scale and slows down the deployment of AI in dynamic, resource-constrained environments. But now, a new paradigm is emerging, one that suggests we can do better by doing less. Recent breakthroughs are proving that we can solve dense prediction tasks by simply reading out information directly from pretrained generative backbones. Imagine a massive library of knowledge, a pre-trained model that has already learned the fundamental structures of images. Instead of building a new decoder for every new task, researchers have found that they can attach a lightweight, task-specific adapter to this existing backbone and simply read the answer directly from its internal representation. This is the essence of the ReChannel framework. By utilizing a shared token-local linear head with merely 33,000 parameters on a frozen backbone, this approach achieves state-of-the-art accuracy on benchmarks like KITTI depth estimation. Remarkably, it does this while being nearly 2.5 times faster than traditional methods that rely on complex decoding pipelines. This concept extends beyond static images to the dynamic world of video. The Genception framework proposes that video diffusion models, originally designed for generating content, can serve as general-purpose vision learners. By repurposing the iterative backbone of video generation, researchers have unified diverse visual tasks within a single model. This is akin to the shift seen in large language models, where a single engine powers everything from translation to coding. The result is staggering. This unified approach matches the performance of specialized models while requiring 700 to 500 times less training data. Think about that for a moment. We are moving from a world where we need massive, task-specific datasets for every application to a world where a single, data-efficient backbone can master them all. Finally, this wave of efficiency challenges our assumptions about how we should verify results during inference. The Flashbow-N framework introduces a surprising twist. Simple best-of-N sampling, a strategy that generates diverse, low-cost draft candidates, actually outperforms complex guided search methods. Under fixed computational budgets, this simpler approach yields an 8% increase in performance metrics compared to its more elaborate counterparts. This suggests that our resources are better spent exploring a breadth of possibilities, rather than getting bogged down in repeated, costly verification steps. The implications of these discoveries are profound for both science and society. For researchers, the validation of readout-only interfaces removes the computational barriers that once made exploring complex data distributions seem intractable. It opens the door to investigating longer sequences and more intricate patterns without the overhead of training new models from scratch. For engineers, this shift provides practical tools for deploying adaptable AI in dynamic environments. Imagine autonomous vehicles that can instantly interpret complex road scenes or medical imaging systems that adapt to new anomalies without requiring a full software update. By leveraging heavy generative priors with lightweight adapters, we are paving the way for AI that is not only more accurate, but also more efficient and scalable. This efficiency gain accelerates the integration of AI as a robust infrastructure, capable of meeting the demands of modern policy frameworks and real-world applications. In summary, we are witnessing a decisive shift toward pretrain-and-read architectures. By reading fields directly from pretrained token lattices, unifying tasks within video diffusion backbones, and optimizing inference through simple sampling, we are unlocking a more streamlined future for computer vision. These findings suggest that the key to advancement lies not in building more complexity, but in smarter utilization of what